Welcome, I'm Ramy Ghoraba, and we're back with a new video from the Ultimate HVAC Guide. Today, we'll discover how an absorption chiller uses thermal energy to produce cooling with minimal compressor power. We'll explore its working principle, main components, and complete operating cycle. Ready? Let's begin. In this quick guide, let's discover the absorption chiller, a smart cooling machine that uses heat instead of relying on a traditional refrigeration compressor. Key idea is simple. An absorption chiller is a heat-driven cooling system. It can use steam, hot water, or direct-fired energy to produce chilled water. This type of chiller is mainly used in medium and large applications, such as hospitals, large commercial buildings, district cooling plants, and facilities with available waste heat. One big advantage is that it reduces electrical demand, especially when waste heat is available. That makes it attractive in energy-conscious projects and cogeneration systems. Instead of compressing refrigerant vapor mechanically, the absorption cycle uses four main sections: the generator, condenser, evaporator, and absorber. To be more precise, absorption chillers do not use a large mechanical refrigerant compressor, vapor compression chillers. They may be direct-fired or indirectly heated by steam or hot water. Capacity can vary widely, often from around 70 to COP is lower than many electric chillers, typically around 0.6 for single effect and around 1 to double effect units. So, when is an absorption chiller a smart choice? When you have available heat, need large-scale cooling, and want to reduce electrical consumption or support a hybrid chiller plant. In short, the absorption chiller is a heat-powered cooling solution, efficient in the right application, especially for large buildings and energy-integrated systems. How can heat produce cooling? Let's discover how an absorption chiller works without a large mechanical refrigerant compressor. Chiller has two main sections. The upper section contains the generator without condenser, while the lower section contains the evaporator and absorber. Heat exchanger transfers heat between the returning solutions, reducing the required heat input and improving system efficiency. Weak solution is pumped from the absorber through the heat exchanger to the generator. Approximately 60% lithium bromide and 40% water. Weak solution fills the generator reservoir, where it becomes ready to receive heat and begin the separation process. Weak solution or hot water supplies heat to the generator, causing the refrigerant water to separate from the lithium bromide solution. Separated water leaves the generator as vapor and flows toward the condenser, while the lithium bromide solution becomes more concentrated. Concentrated solution flows back through the heat exchanger, releases part of its heat, and returns to the absorber to repeat the process. Tower water removes heat from the condenser, changing the refrigerant vapor back into liquid water. Condensed refrigerant collects in the tray, flows down to the evaporator, and is sprayed over the chilled water tubes. Under deep vacuum, the refrigerant water evaporates at a very low temperature, absorbing heat from the chilled water loop. Under chilled water loop carries the cooling effect to the building, supplying air handling units and fan coil units with cold water. Heat drives the process, and the cooling cycle continues, elated and sprayed again, and the cooling cycle continues.